Okay, we have now studied and learned about the fundamental theorem of calculus. So, if you've been following along since the beginning of the course, you knew that we began by talking about functions, and then calculus starts when you get into the idea of limits, and then we use limits to first talk about the slopes of graphs, which is the derivative, and we use that for all sorts of things, related rate problems and optimization problems and graphing, sketching graphs of functions and so on. And then, just of late, we've also used limits to talk about the areas underneath curves. And recall that limits were used for both of these things. Limits were used for derivatives because we said let's find the slope of this secant line, and then we'll take the limit as this point gets pushed into this one, and we'll get the slope of the tangent line in the limit. So that was that one. And then for the area underneath the curves, we did something kind of a similar spirit. We said here's a function from A to B, and we want to find the area underneath that function above the x-axis. So we'll take a bunch of rectangles, and we'll find the areas of those rectangles, and that's an approximation for the area underneath the function. And then we'll take the limit again as the size of these little intervals go to 0. And as that goes to 0, then you end up with the actual area. And then that was areas. And then we discovered this kind of amazing theorem which connects the two, the fundamental theorem of calculus. Okay, which says that if you have a function like this and you want to find the area of it underneath it, you just find the antiderivative, and evaluate that at the endpoints, and that'll give you the area, which is really kind of amazing. So there you go. So that's what we've done so far. Calc 2, by the way, what we're going to do in the next couple lessons of Calc 1, just to finish the course, is we're going to learn a few more ways to find antiderivatives. Okay, antiderivatives. And we're also going to see how they can be applied to area problems. Okay, so that's just a quick introduction of being able to find more antiderivatives and applying them. And then what Calc 2 does is it takes this and really runs with it. You find a whole lot more applications of integrals, and also you find a whole lot of more ways to find antiderivatives. And so you do that, and then you get into another whole area called sequences and series, and sometimes differential equations. Kind of depends on the course. But anyway, that's what comes up in calculus. So to finish up Calc 1, which is this particular course, there's two things I want to do. First is I want to find then the area between some graphs. So let's take this as the first example. Let's say that this is the graph of the square root of x, and this is the graph of x squared, right there. And it's easy enough just to notice from inspection that they intersect at the point 1, 1, because when x is 1, y is 1, and when x is 1, y is 1. So suppose we want to find the area between these two graphs, okay, which would be, here's 1 right here, here's 0, and so we're trying to find the area of that region right there. How could we do it? Well, one way to do it would be to say, let's first find the area underneath this larger graph, or I should say the higher graph, the one that's taller, higher, greater, farther away from the x-axis. And so that is the square root of x. Okay, so if you first find the value of this, that's going to be the area underneath the square root of x function. So it would be all this stuff right here. Okay, all of that stuff. And then you subtract off the stuff under the parabola, under x squared. So you get rid of this stuff. So if you subtract this, then that should give it to you, right? That should give it to you. So that's one way to think about it. Another way to think about it, if you just use one of the properties of integrals that I mentioned to you, I think already, is that you can break this thing up, or you can pull them together as long as these limits are the same. And you can combine them into one integral, okay? So you can either break it up, you can pull constants out front, same as you can do with derivatives, okay? So this is equal to this. Now, what is this geometrically? Geometrically, if you think about it, what this is saying is for every value of x, I just think of this as a tiny, tiny little sliver. We're adding up all these slivers. So at a particular value of x, what's the area of the sliver that you want? The sliver is going to have a thickness of dx, that's the thickness of it, and the height of it is going to be, for this particular value of x, the height of it is going to be the square root of x minus x squared. That's exactly what you have here. The square root of x minus x squared. So if you start at 0 and go to 1, and for every value of x between there, you take the square root of x minus x squared, you're going to be getting that height all the way around, all the way through, and you add up all those contributions, and that should give you the area. So let's go ahead and do it. This is x to the 1/2 power minus x squared. And so now the antiderivative is going to be x to the 3/2 times 2/3 minus x cubed times the divided by 3 is going to be 1/3. Now from 0 to 1, you stick a 1 in here, you're going to get 1 to any power is 1 times 2/3 is 2/3. Put a 1 in here, you're going to get subtract 1/3. And then when you put a 0 in both of these, you're going to get 0 minus 0. So you end up with 2/3 minus 1/3 is 1/3. So there's the area between those two graphs. Okay, let's try a couple more. Let's say we've got this function right here. Here's the sine of x from 0 to pi. And let's take y equals 1/2, which is just that straight line right there. And suppose this is what we're after. Suppose we're after the actual area of this region right there. The area of the region between these two curves from 0 to pi. See that? All shaded in there? That's what we're after. Okay? So we have to be careful here because, again, you have to remember you're always adding up these little heights of rectangles. So first of all, we need to find out where these points of intersection are. So where is the sine of x equal to 1/2? Well, I just happen to know my trigonometry, so I know that's going to happen at pi over 6 and at 5 pi over 6. So this point right here is pi over 6, and this point right here is 5 pi over 6. Okay, go back to one of our first lessons in trigonometry if you need to for that. So now, what's the area that we're looking for? Well, from 0 to pi over 6, notice that we're adding up all these little rectangles, and the height of each rectangle is going to be the height of this function, which is namely 1/2, minus the height of this function, which is sine of x. And so we're going to add up all those contributions from 0 to pi over 6. See that? Then, from pi over 6 to 5 pi over 6, we're going to add up all these rectangles. What are these rectangles? For every value of x in here, we're taking this value minus this value, which is going to be sine of x minus 1/2. From there to there. And then finally, from 5 pi over 6 to pi, we're again going to take 1/2 minus sine of x. Okay, there you go. So we could calculate that whole thing, but let's save ourselves a little bit of work. Okay, there's some symmetry here. Let's take advantage of some symmetry. Notice just from the symmetry, this region is exactly the same as this. This half is exactly the same as this. So instead of evaluating this, let's just do 2 of these. And instead of going from pi over 6 to 5 pi over 6, let's just go from pi over 6 to the midpoint here, which is pi over 2. And then we'll take 2 of those. See that? So I basically, now we're just looking at this region right there, and we're just going to double it. And by doubling it, we're going to get what we want. Okay? So let me just get rid of that. Okay? So that's what we're after. And so now, what can we do? Let's see. So this is going to be 2 times. What's the antiderivative of 1/2? It's going to be 1/2 x. The antiderivative of negative sine is a plus cosine. Agreed? The derivative of cosine is negative sine. So we've got that. So from 0 to pi over 6. And then, let's see. Okay, I'm just going to have to kind of pi over 6 right here. Plus, same thing here. 2 times. The antiderivative of sine is a negative cosine of x. And then the antiderivative of a negative 1/2 is negative 1/2 x. We're going to evaluate that from pi over 6 to pi over 2. Okay, so now it's just a whole bunch of inserting things. So if you stick a pi over 6 in here, first of all, let's keep the 2 out front. Put in a pi over 6. You're going to get pi over 6 times 1/2 is going to be pi over 12. Plus the cosine of pi over 6. I should have left this up here. Pi over 6. The cosine of it is square root of 3 over 2. Okay? Minus what happens when we stick in 0. So put in a 0 here, you get 0. Put in a 0 here, the cosine of 0 is 1. So it's going to be plus 1. So I've got this whole thing there, times 2. 2 times this whole thing. Okay, plus 2 times this whole thing. What are we going to get? Cosine of pi over 2 is 0, so that's going to be negative 0, minus pi over 2 in here, you're going to get negative 1/2 times pi over 2 is going to be negative pi over 4. Subtract, put in a, this is a pi over 6 there, put in a pi over 6. The cosine of pi over 6 is square root of 3 over 2 times negative is going to be negative square root of 3 over 2. And then this is going to be negative pi over 12. You see, the hardest part here is just keeping track of all of your negatives and such. Okay, let's see how well I did. So, so this is going to be, if I multiply it by 2, I'm going to get pi over 6 plus square root of 3. And then here I'm going to get minus 1. So minus 1 times 2 is going to be minus 2. Okay, so there's that portion times 2. And now what happens over here? Let's see, I'm going to get 2 times negative pi over 4 is going to be negative pi over 2. Here I have negative of a negative is going to be positive. When these 2 cancels, I'm going to get plus square root of 3. And then finally, I'm going to get negative of a negative is positive again. Positive pi over 12 times 2 is going to be positive pi over 6. Okay, so what do we end up with? We end up with 2 2 times the square root of 3. Here's pi over 6 plus pi over 6, which is pi over 3. Pi over 3 minus pi over 2 is a minus pi over 6. So that takes care of all those. And then I finally have minus 2. Okay, so assuming I made no mistakes there, that's the answer. Let's see. That's roughly square root of 3 is like about 1.7, something like that. So that would be about like 3.4, and then you're subtracting 2, and then you're also subtracting about 1/2. Pi over 6 would be roughly 3 over 6 would be about 1/2. So it'd be roughly 3.4 minus 2.5 would be roughly 1. So basically, it would say that the total area underneath that thing would be roughly 1. And that seems kind of reasonable because the total area under this whole graph was 2. And so we've got this stuff instead. So that's roughly 1. So yeah, that seems reasonable. Okay, so there you go. Okay, let's do one more. Each one of these kind of shows some various important ideas. Let's say we've got this function. I shouldn't call it a function now in this case. We've got this situation. So this right here is y is equal to the square root of x. This right here is y is equal to the negative square root of x. Okay, so this is the graph of x equals y squared if you wanted to write it in terms of like this. So it's a parabola that is on its side, and this right here is the line y equals let me see here, x minus 2. X minus 2. Okay, so that goes down there, that hits right there at negative 2. Okay, and we want to find the area of this region right here. Okay, all this region, the stuff that's enclosed between these graphs. So again, let's just start. You're going to see why in a moment. We better find these points of intersection. So this one's easy enough. If y is equal to 0, x is equal to 2, so this is the point 2, 0 right there. To find this one and this one, let's see, how can we do it? X is equal to y squared, and y squared is going to be x minus 2 quantity squared. So that means x is equal to x squared minus 4x plus 4. If you bring the x over to the other side, you're going to get x squared minus 5x plus 4. And 0 is our friend. This factors into x minus 4 times x minus 1. Agreed? That multiplies to this. So this tells us that the points of intersection are when x is equal to 1, namely 1, and if x is 1, then y is, well, y in this case would be negative 1. And up here, when x is 4, then y would be 2. So here's the point 4, 2, right there. Okay, and you can check it out. If x is 4, then y is going to be 2. If x is 4, y is going to be 2. Okay, so now that we have those points of intersection, let's think about what we need to do. We are adding up all of these rectangles. See this? There's a rectangle. There's a rectangle. There's a rectangle. There's a rectangle. All these rectangles we're adding up. And so never lose sight of what you're doing. Okay? You never want to become mechanical. You always have to picture what you're doing. So, do you see what's going on here? From here to here, we're adding up rectangles such that the larger value is this one and the smaller value is this one. So the area is going to be from 0 to 1, x starting at 0 and going to 1. The larger value is the square root of x, and then we're subtracting the smaller value, which is negative square root of x. And we're adding all those things up. Once we pass 1, then from 1 all the way to 4, from 1 all the way to 4, here's 4 right here, what are we doing? The larger value is now the square root of x again, and the smaller value is no longer this function. We're starting here at the square root of x and we're going down until we hit what? Until we hit that function, x minus 2. Okay, dx, sorry about that, from 1 to 4. Okay, so how do we evaluate that? Well, let's go ahead and do it. Notice here we've got a double a negative, so I have 2 square root of x, so I can bring that 2 out front, and I go from 0 to 1, and I'm going to write that as x to the 1/2 power. I'm going to do a couple steps in one. Okay, you see what I did? Minus negative is 2 times the square root of x. I bring the 2 out front, and so I have square root of x. Square root of x is the same as x to the 1/2. Plus 1 to 4. I'm going to get the square root. I'll write that as x to the 1/2 again. And then minus x minus the negative is going to be plus 2 dx. Okay, let's evaluate it. If I evaluate this, it's going to be x to the 3/2 times 2/3. 2/3 times 2 is going to be 4/3. Evaluated from 0 to 1. Plus, when I do this, same thing. It's going to be x to the 3/2 times 2/3 minus 1/2 x squared. Agreed, the antiderivative of that is 1/2 x squared plus 2x. And that whole thing is evaluated from 1 to 4. So you stick in 1 here, you're going to get 1 to any power is 1, you're going to get 4/3. Stick in 0, you're going to get 0. What happens when I stick in a 4 here? Square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16/3. So you're going to get 16/3. Put in a 4 here. 4 squared is 16. 16 over 2 is going to be minus 8. Plus, put in a 2 here. Put in a 4 here rather. You're going to get plus 8. Minus what happens when you stick in a 1. Here you're going to get 2/3 minus 1/2 plus 2. What does that all end up giving us? Well, let's see. How many thirds do I have? I have 16/3. 20/3 minus 2/3 is going to be 18/3. 18/3 is the same as 6. So all these things just end up giving me 6. These go away totally. Here I'm subtracting 2, so it's going to be minus 2, and I'm going to be adding 1/2. So that's going to be 4, 4.5. 4.5 is the same as 9/2. So there's the area underneath that, I should say, between those two graphs. Okay? So that takes care of that, but let me show you a much easier way to do it. Okay? Remember that 9/2 is our answer. And let's think outside the box here for a second. Everything I've been teaching you, we've been doing everything with little dx's, right? We've been doing everything with dx's, and we've been having little rectangles which go up and down. But there's no reason for that. It's convention, it's kind of what we're used to. But we could just as easily add up all these little rectangles going this way. And look how much easier it's going to be if we do it this way. Look, watch this. Here's the area. First of all, instead of writing this in terms of, we're gonna put in instead of putting in an x value and getting a y value, we're going to put in a y value and get an x and get an x. So the value of the function is now going to be how far off you are in this direction. It's going to be the value of x. So we already had here that x is equal to y squared. So that's that one right there. If we solve this one for x, we're going to get what? Add 2 to both sides. We're going to get x is equal to y plus 2. See that? So think about it. From here to here, starting at the bottom and going up to here, look at what we're doing. We're taking, for every value of x, for every value of y here, we're taking the bigger value of x, that's this one right here. For every value of y, we're taking the bigger value of x minus the smaller value of x. There's the smaller value of x. That's just that. See this? For any value of x, this tells you, if you give me the y value, this thing tells me what the x value is. If you give me the y value here, this equation tells me what the x value is. Okay, let me do that one more time. For any particular y value, this equation tells me what this x value is. There it is. It says, what does it do? It says take the y value and add 2, and you're going to get this x value. What does this one say to do? It says take the y value and you square it, you're going to get that x value. So for any value of y, you take this value, which is that, minus that value, and you're going to get this length. You add up all those lengths from this value of y, which is -1, to this value of y, which is 2, and look how much easier this integral is. Wow, look at here. The antiderivative is going to be 1/2 y squared plus 2y minus 1/3 y cubed. Integrate from -1 to 2. Okay, just one integral, simpler stuff, no square roots, all that kind of stuff. You throw in a 2 here, what do we get? 4 over 2 is 2, plus 2 times 2 is 4, minus 8/3. Now you put in a -1. -1 squared is 1, so you're going to get a positive 1/2, and you're going to get a -2, and here you're going to get a -1/3 times negative is going to be, well, let's see. Yeah, negative times negative is going to be a positive 1/3. Okay, you still have a negative there as well. What do we get? We're going to get 6 plus 2 is going to be 10. Then we're going to get, here is -8/3, and here is another -1/3, which is -9/3, which is minus 9/3, which is -3. And then finally, we're going to have a -1/2. So 10 minus 3 is 7. 7 minus 1/2 is 6.5. Dang, is 6.5. 6.5. Where did I make a mistake? I remember that the answer is 9/2, so I made a mistake here someplace. Okay, you've been with me all course long, so see if you can find it for me. We're going to have y plus 2 minus this thing from -1 to 2. Okay, so the antiderivative is going to be 1/2 y squared plus 2y minus 1/3 y cubed. Okay, we do all that from -1 up to 2. Sticking a 2 here, you're going to get 4 over 2 is 2. 2 times 2 is 4. Here you're going to get 2 cubed is 8/3. So that's all correct. Minus, now you put in a -1. You're going to get a 1/2 here, a -2 here, and a negative times negative is going to be a positive 1/3 there. Okay, so let's just add them together one more time. I'm going to get 6. Oh, 6 plus 2 is 8. Did I have 10 there? 6 plus 2 is 8. Okay? Then you're going to subtract 9/3 is going to subtract 3. And then you are going to subtract 1/2. There you go. 8 minus 3 is 5. 5 minus 1/2 is 4.5, 9/2. There was, I think I had a 10 there. So there you go. Okay, so there it goes both ways. Pretty cool. So those are area problems. And what's coming up, we're going to see one more way of doing some kind of interesting antiderivatives. And then we're also going to have a review. And that'll be the end of this course. Very good.